Welcome to In 5 Minutes. In the previous video clip, we discussed the flywheel effect, in which we had concluded that if we apply current pulses of varying amplitudes, then I can generate the oscillations in the tank circuit which are proportional to those amplitudes of the current pulses. And then we had said that if I can generate the pulses from the modulating signal, then pulse amplitudes will be proportional to the modulating signal, and hence the oscillation that I generate will be proportional to the modulating signal, and that will become double sideband full carrier AM signal. So now let us discuss how to generate pulses from modulating signal. To generate pulses from the modulating signal, we will take one very important circuit which is called Class C amplifier. The Class C amplifier, in very simple form, using BJT, will make use of negative power supply on its base. So when we give negative supply to the base with respect to the emitter, in that case we are biasing BJT below the cutoff. Now if you remember, between base and emitter there is nothing but the PN junction diode. I've taken NPN transistor, and hence I can always define the base current which gets generated as a function of the base emitter voltage. And we all know that for any PN junction diode, only when the voltage across the diode crosses something called as the threshold voltage or the cut-in voltage, which comes out to be 0.6 volts to 0.7 volts. Let me take 0.7 volts here for silicon transistor. In that case, only when the cut-in voltage is equal to or above 0.7 volts, then the current will be flowing through the junction. There's a conduction taking place through the junction. If the voltage is below 0.7, then we say that the PN junction is reverse biased. It is not biased in forward mode, and hence the current that will be flowing through the junction will be zero. The forward current, to be precise, will be zero. So when I give negative voltage to the base, which is of P type, which is the anode of the PN junction, because this is NPN transistor, emitter will be the cathode of the PN junction. You can simply look at this base emitter as nothing but a PN junction. So because anode is at negative potential compared to cathode, I say that we are biasing the transistor below cutoff. So let's say this is my Q point below the cutoff. If that is the case, then base emitter is reverse biased, and if the base emitter is reverse biased, that means the transistor is in cutoff, and the output current, the IC, the collector current, will be zero, and the voltage, the AC voltage across RC in that case will also be zero. When we apply sinusoidal signal on the base, which already had the negative DC supply, let's see what will be the resulting base voltage. So the first waveform that we have taken here is nothing but my sinusoidal signal that we have taken. Let me call it Vs, and let's say the negative supply is VBB, which is represented using a red line here. So if I write the total base voltage, let's say VB or VBE, because emitter is already at ground, the total base voltage will be sum of sinusoidal signal and negative DC signal. When you add negative DC signal to the sinusoidal signal will shift down by a level equal to the negative DC signal. So you can see the waveform which I have drawn in the second plot, the black line will be nothing but the overall voltage generated on the base of the transistor. You can see the first waveform is shifted by the amount equal to VBB. Now let us talk about the conduction of transistor or the conduction of base emitter region again. We said that the transistor is biased below cutoff with the help of negative supply, and as long as the base voltage will be negative or below cut-in voltage, the transistor cannot conduct. If I assume transistor to be ideal, then the voltage at the base has to be greater than 0 and may not be greater than 0.7 for base emitter to be forward biased and for transistor to conduct. So you can now see that the resulting voltage at the base remains below zero most of the times, except when the sinusoidal signal takes its peak values. Those peak values are good enough to be above the zero level, because those positive peak values, when get added to the negative DC supply, the overall base voltage, the overall VB is positive. The base emitter will be forward biased and the BJT will conduct only for this small peaks in which base voltage becomes greater than zero. And whenever BJT conducts, there will be corresponding collector current, and if you take the output voltage VO across RC, you will get the output voltage that will be in the form of pulses. What happens to output voltage in between the two pulses? You can see in between the two pulses, the base voltage is negative, it is below zero level, and hence BJT remains in cutoff, and hence output is also zero. So class C amplifier is a circuit which will help us to generate pulses from the original sinusoidal signal. So this sinusoidal signal will be my modulating signal, and the modulating signal will be converted into the pulses, and the pulses will be nothing but proportional to the peaks of the signal. And this pulses, when you give to the tank circuit using flywheel effect, we will generate oscillations of amplitudes equal to the pulse amplitudes, and hence proportional to the amplitude of the modulating signal.